In this lesson, we want to focus our attention on introducing the processes associated with working with images in Matlab. But before we can get started with that, let's do a basic overview of understanding how we work with images and other components of data that are represented. And so we've thus far worked with logicals where we recognize that a value will either be true or false, and that in turn is represented by computers as a 1 for true and a 0 for false. We've also worked with other numbers, and we have different base systems, whether it's base 10 or base 2, 4, and 8, and how those are represented on computers for binary base 2 or tens and hundreds and thousands for different bits. We also have various characters that we can utilize, and our ASCII characters vary from capital A to the end of the alphabet, then to lowercase a to the end of the alphabet, and then characters for 0 through 9 as well. And the ASCII code representation can also be represented in binary by computers. And so now we want to explore how we represent images. And so when we see an image, we see a combination of various colors that will normally represent some type of scene or some type of object that we're used to. But how exactly is that represented on a computer? And so let's consider the basic building blocks of an image. Each picture is composed of various pixels, and a pixel can be essentially representing the foundational building block of an image. And so the pixel is the smallest addressable element that we can have in an image. And we're going to represent pixels by using specific coordinates. We'll use essentially 5 values to represent 1 pixel. And we'll have a R coordinate, a C coordinate, and then we're going to have a color value. And the colors are based upon a red value, a green value, and a blue value. So if we take a look at the image that we have here, and we wanted to represent one of these green pixels, we would have first a component for the red value. And the red value is going to be represented with the R coordinate and C coordinate. So that's going to be 5 for R and 6 for C. And then we have the red value. So in this case, we'll have a 1, and that is going to equal to 0. Next, we'll have the green value that is represented. And the green value is going to have R and C of 5 and 6. And we have a 2 here. And the assigned value is going to be 255. And then we'll have a blue value. The R and C are the same. And 3 is denoting that it's just the blue value. And the assigned value for this component is 0. So what we see here is that we have red values of 0 and blue values of 0 and a green value of 255. And that means that this pixel is a completely green pixel. And so those are essentially the 3 components that will make up a pixel image. And so let's dive a little bit deeper. And so when we've broken colors into our color spectrum that is going to be represented as a triad as red, green, and blue. And this is because these are the primary colors of light. The values that we have for each one are going to go from 0 to 255. And so let's get into a little bit more detail about why those specific values are used. In order to represent a color, a pixel on the color spectrum for red, green, or blue, we're going to use a unsigned 8-bit integer. And this means that when we say an unsigned number is going to either be 0 or positive. So when representing colors, we can go 2 to the 8, which is going to mean that we can start with the value of where all of the bits are 0. And so we start at, that's going to equal to 0, or all of the values are 1, and that's going to go to 255. So the range in the color values that we can choose for our RGB components are going to be from the values of 0 up until 255. 255 is the max. And so that means that we can pick between 256 different values for each RGB component. And so this means that there allows for various values that can be used to determine a color. So if we have a color that is completely red, that means that the R value is going to be 255. The green value is 0, and the blue value is 0. Now let's consider if we want to have a value that is completely green. In that case, our R components and our blue components are going to be 0, and green is going to be 255. That means that it is a completely green color. Let's consider if we have something that is solidly blue, then R value is 0, and green value is 0, and our blue value is 255. And so that means that when we have different combinations of values for um, representing a color, we're going to have different values here. It doesn't always have to be 0 or 255. So for example, for a solid yellow color, we'd have 255 red, 255 green, and 0 blue. And we can have various other combinations too to represent the entire color spectrum. So if we wanted to have a very, very light gray, that means that all values for RGB are going to be 255. And so this allows for different options in terms of picking the color that would be used for representation. And so there are a number of tools that are available online that you can use to play with and see how different colors can be picked. And so W3 Schools does have a RGB color picker that will allow for you to determine different colors. So let's say if we want to set the R component to a value of 113, the green component, we might not want it to be all the way 255. We can set it to 210, and then we can set the blue component here, and we can make it a little bit darker. And so this allows for you to pick and choose different colors. And so with this, in case we're able to see that we set the blue value lower, the green value a little bit in between the possible range, and red is a little further. And that's how we derive from a solid, if we had this all at 0 here, that's how we derive from going to a red to kind of like an orange. And so when we combine more and more of the green component with the red, we start getting into yellow. And as you can see, our RGB values are represented here to showcase, to show you the differences that are made. And again, if we wanted a solidly green, we increase all the other components, bring our RGB down to 0 for R and B. And if we wanted to make this a little bit darker, we can do that by increasing the blue. And then we can increase the red to make it more of a teal or light green color. And so there are different ways in which you can kind of just play around with the colors. And that's an exercise that you can do on your own to see how changing the values for RGB will affect the actual color that comes out. And so here we are able to see how the variation in the values for RGB affect the different colors that we use. And typically in most design components, you'll have a color picker that will allow for you to pick the different colors that you want to use. And so what we want to do is keep in mind that each pixel can only define one color. So the more pixels that you have, the better your recreation of the image will look. And so here we have an example that shows how various pixels come together to create an image. With our image on the left, we can see the grid, or on the right, we can see the grid that can be utilized. But this also goes into great detail about the importance of our computing systems and how important memory and bandwidth are in making graphics better. So decades ago, when our computing systems weren't as powerful as they are now, images and animations would appear very pixelated and very much dot matrix style. But now with improved technology and quicker processing speeds, we can have more uh, graphics that are more realistic and that in a way look more human-like. The same applies for films and movies as well. The more bitmap graphics were the prevalent form of image creation in the 80s and 90s, but now we have more advanced technologies, so we can have better looking graphics to go along with that. And so we want to keep in mind that for each pixel that you use, Matlab is going to represent it as a three-dimensional array for each layer. And what we mean by each layer is the R, G, and B components. And of course, we have the row and column coordinates that are utilized. So for this one pixel here, sorry about that. For this one pixel that has the R and C coordinates of 1 and 1. So again, the 1 in our third position represents that this is the red component. The 2 means that this is the blue component, and the 3 is going to be the green component. And so with a value of 255 for the R component and 0 for the green and blue components, we know that this is going to be a solidly red pixel. And so for illustrative purposes, we can see in a grid how this is represented, with red being 255 for 1, 1. So let's look at another pixel. So now we're on our furthermost coordinate of 1, 1 for red. If we want to look at coordinate 2, 3 here, then we can see what values are used. And for this pixel, for the red component, we have a value of 0, and that is here in our red matrix. For the green component, we have a value of 255. And then for our blue component, we also have a value of 255. So you want to note that this is kind of a combination of green and blue together. And so because we have our maximum value for both of the green component as well as the blue component. And so this again goes back to the different combinations that you can have in picking different layers. So if we want to go to our purple color pixel, which is in position row 2, column 2, right here. And so the red component is 255. The green component is 0, and the blue component is 255. So that is a combination of the maximum red and blue values to create this purple hue. And so different combinations can be utilized to create the various colors in our color spectrum. So this provides a high-level overview of working with or understanding the concepts associated with pixels and images in Matlab. Next, we'll work through a few examples in Matlab to show how we would work with these values in working with an image.